It is visible now.
Right, thank you for the input. So good afternoon, everybody. Last class we started with the chapter on association rule mining. We went over the basic concepts. That is, we introduced ourselves to what is an association rule and what do we mean uh, by the term frequent item set, right? We defined what is an item set, what we defined what is a frequent item set. Then we went over to a metric called the support. We saw two variations of that, that is the absolute support count and a fraction, which we call the support. This is the total number of transactions that contain a particular item set divided by the total number of item sets which are I'm sorry, total number of transactions which are present in the entire data set. Okay. Now, what is a frequent item set? Frequent item set is a item set whose support is greater than a threshold value which is given by the user, right? We had also discussed why this uh, mm, threshold is kept a subjective measure and what are the pros and cons of the same, right? Thereafter, we saw another stronger metric to evaluate the interestingness of the association rules, namely the confidence, and we discussed the formula for confidence, right? Now, after that, we had started talking about the task of mining association rules, that is, generating the association rules, right? So, we had already agreed that it will not be possible for anybody to generate all the association rules from a given data set, right? Why is that? That is because it would be very computationally prohibitive, right? Now, these thresholds, interestingness thresholds, or the metrics that we had decided for ourselves to evaluate a association rule upon, that is namely the support and the confidence, even these don't help up till now, right? Why? Because what we are planning to do is we are planning to, in the very brute force, that is the basic approach, we are planning to generate all the rules, then see which one of them have the threshold support greater than the threshold specified by the user, and confidence greater than the threshold specified by the user, right? Now, but we got stuck in the very first step, that is the generation of all association rules. So, as an example of that, please see here. For example, I have this transaction database with me, and I want to generate the rules from a single three item set. Okay, this three item set is milk, diaper, beer. Okay. How many rules are possible? Please see 3C2, 3C2, right? I want to do, what do I want to do? Actually, whenever we want to generate an association rule from any particular item set, what do we want to do? We want to divide this item set into two partitions such that one partition occurs on the left hand side as the antecedent of the rule, and the other partition occurs on the right hand side as the consequent of the rule, right? And we must ensure that these two partitions don't intersect each other. Okay, that means their intersection is empty. So, if suppose I'm talking about, let's say, a four item set, okay, or a 3-item set, then no item can be on both the sides of the rule. Why is that? Because if I were to produce a rule saying that milk and diaper implies milk and beer, it would be so trivial. Since milk will always imply milk, there is no point in generating such a rule, right? So we ensure that no item is on both the sides of the rule. So we generate the binary partitions. Binary partition means two partitions of the item set from which the association rules are to be generated, such that the two partitions are empty. Their intersection is empty. Okay. Now, from this item set, for example, how many binary partitions can I make? 3C2? Is that right? Yes or no, students? Which is equal to 3 factorial divided by 2 factorial into 1 factorial, right? Which gives me 3, right? So what are the basic partitions that I can generate from this item set? They are milk, diaper and beer, right? Milk, beer and diaper, and then diaper, beer and milk, right? So correspondingly, we generate these three rules first of all from the item set, 3 item set that we are given. Okay, can you see this? Right? Now, what are these other three rules? Well, these are these first three rules turned around. Okay, that means from this first binary partition that I did from this item set, let's say milk, diaper and beer, I divided into milk, diaper 1 and the second partition as beer, then milk, diaper implies beer is the first rule, and what will be the second rule? Beer implies milk, diaper, right? So the other three rules are just the opposite of these rules, where the antecedent become the consequence and the consequence become the antecedents. Okay. Now let us find out the support and confidence of all these rules. Can you find out? Can you please find out how many times does milk, by diaper and beer appear together? Let's see. Milk, diaper and beer, right? Milk, diaper and beer 1. Milk, diaper and beer 2. Milk, diaper and 2. Only 2. 2 out of 5, which is 40% or 0.4. Right? This is the support for milk, diaper and beer. And what would be the support of this rule now? Beer implies milk, diaper. It would again be same. Please see, because we are in general looking for the transactions which contain these three items, and the order in which these three items appear in these transactions is not important for the support, right? So again, this would be 2 out of these two transactions out of 5, which gives me 40% support, right? So you will observe that for each association rule that we have here, its opposite will always also have the same support. Okay. However, is the same true for confidence? Well, let's see. Let's see it with the example of the first rule again. So what is the confidence? Confidence is simply the number of transactions which contain milk, diaper and beer divided by the number of transactions containing milk and diaper, right? So, however, when I invert the rule, the confidence would be the number of transactions containing beer, milk and diaper, which would be same as the previous rule, but it will be divided now by the number of transactions containing beer, which may be different from the number of transactions containing milk and diaper. So the denominators are different, and you see, by chance, for this rule the confidence is same, but for the second rule, you see here, milk beer implies diaper and diaper implies milk beer. For this set of rules, the confidence varies. Their support is still same, but the confidence varies. Yeah. So support is commutative, whereas confidence is not. Okay, so this is again an important question that is asked sometimes, that is support commutative? uh, what do you think about the confidence? Okay, or sometimes you're asked to compute the support and confidence and show which one of these is a commutative measure. Okay, now let us go back to the task of generation of association rules. We have just seen that the support of the items, the association rules, I'm sorry, remains the same even if I invert the association rule, right? But the confidence does not. Okay. So as far as I'm keeping the item set same, the support of all the rules that will be generated from this item set will be same, right? So what we are going to do is that we are going to divide our process of mining the association rules into two parts. Okay, the first part would be the generation of only frequent item sets. Okay, so that means that I will not need to generate association rules from all item sets now. Okay, only the item sets which are frequent. Is that right or wrong? What do you think about this? I gave you a task to think about how to make the process of association rule generation computationally non-prohibitive. Do you remember that? Do you remember that, students? So, did anybody do some thinking on that? Well, this is the idea. This is the idea by which we will not now require to generate all association rules. Rather, we only generate the rules from the frequent item sets. So, since obviously the number of item sets which are frequent will be much less than the entire set of item sets, right? So, the number of rules which will have to be generated are cut down tremendously. Okay. Now, so the two-step approach for mining the association rule becomes that we first just generate the frequent item sets, and only from these frequent item sets we generate the rules, and these rules then we check for the confidence. So out of these rules, whichever rule satisfies the minimum confidence threshold, those rules are selected as good rules or a proper rules or interesting rules. Okay, only those rules are selected and presented to the user. Okay, now all said and done, this seems so good, but there was again a problem that we faced here, and the problem was that this first step, that is the generation of the frequent item sets, itself is a very computationally expensive process. Okay, now why is this? Let us see. So suppose I have D item sets, D items, I'm sorry, in my transaction. That means if D is equal to 6, then I have only 6 items in my store for which I want to find the association rules. Okay. How many possible frequent item sets might be there? Can you think about that? From only this set of 6 items, items means one item sets, can you think about how many possible uh, combinations I can make? And each of these combinations may be frequent. Yes. First, we will generate the from, let's say, on your slide, for example, you can see this lattice for D is equal to 5. So suppose I had initially only 5 items, namely A, B, C, D, E, and from which I needed to generate all the item sets, the frequent item sets. So first I will generate all the 2 item sets, then 3 item sets, then 4 item sets, and finally the 5 item sets, right? How many of these will be there? This entire lattice consists of 2 raised to the power of D item sets. Okay, if we ignore the null set, this comes out to be 2 raised to the power of D minus 1 valid candidate sets. Candidate item sets means the item sets which are likely to be frequent, means they might be frequent, they might not be frequent, but we need to check them, right? So we need to do the computation, we need to process all these number of item sets to determine this first step, that is the frequent item sets. And then from each frequent item set, we will generate the rules just like we did for this particular item set. Then we will evaluate each of these generated rules for the confidence, right? So now, as you can see, this is again a very computationally expensive process. So what to do? What to do? Is there something else that we can do to prune this, to limit this space? Can we reduce the candidate item set somehow using some property, some other heuristic, some other intuition? Well, to our rescue comes in the a priori property. To our rescue comes in the a priori property. Before I go up, before I go there, let us just see again the complexity, the complexity of generation of the frequent item set. Okay, so please see, if these are my transactions, right? Let's say we have n number of transactions, and let's say we have an average width of W of these transactions. Okay, and the list of candidates, that means this 2 raised to the power of D that we computed here, is symbolized by n. Okay. Now, what would be the complexity of this process? Please see, to generate the support count, that means to count the support of each item, what do we have to do? We have to pick that item, for example, bread. Let us, we will first look at the first transaction, right? Now for this entire transaction, we will keep on picking an item, right? And go through the entire list of transactions to count the support for bread. Yes. So what will I do? I will say bread and then I go over all n transactions, right? And I do this for the entire width W of this transaction. Yes. So how many times, what is the complexity of this step that I've talked about? It is order of n W, right? Now, since we must do this for all the candidates, the entire complexity becomes order of NWM. Yes, right?
Yes, ma'am.
But we just said that n was equal to 2 raised to the power of d. Remember? So you can see that this would be so very expensive, right? Even our order of n square becomes very expensive, and here it is becoming equal to 2 raised to the power of d. Okay, so again we come to the same point that can be in any using any property, you know, reduce our problem of this frequent item set generation. Can we make it computationally possible? So as is visible from this formula, one way to do this would be to reduce the list of candidates. Okay. The other would be to reduce the number of transactions. Well, the number of transactions nobody would like to reduce when we are talking about some, store or somebody. Everybody is operating their business because they want to increase the transactions, right? And the same thing goes for W. Nobody would like to reduce the width of a transaction, right? The number of items that a customer is buying. But when we talk about the reduction of number of transactions, and here what we mean is not the literal reduction in the number of transactions for a particular store, but the number of transactions that we have to process in one go. Okay, so sometimes there have been some techniques which have been proposed, which are also known as the vertical partitioning techniques, wherein what is done is that the complete data set, if it is too large, then it is divided into various parts, uh, and only a size that fits in the RAM is taken into the memory. Frequent item sets only from that particular amount of transactions are first computed. They are called the local item sets, local frequent item sets. Why local frequent item sets? Well, because uh, item set may be just, let's say, considered only 10 transactions out of the total 100, and in those 10 transactions a particular item has been bought, let's say in every transaction. Okay, so the its support count is 10, तो अभी तक उसका support is 100%. But when I look at the other transactions, that support may hold or it may not hold. Okay, so that led to the concept of local support and global support. So every time a new partition was taken into the memory and the supports were computed. But these details are not very necessary from your syllabus point of view, only uh, for your, you know, FYI, I've just uh, indulged here. What we are most interested here is either the first case, that is the reduction in the number of candidates, or the number of comparisons that must be done. Okay. Now, a priori property is a property. It was a landmark algorithm, and I think you will take pride in knowing that uh, a person of Indian origin, Mr. Rakesh Agrawal, who's also sometimes referred to as father of data mining, okay, proposed this algorithm in 1990s, in early 1990s. And at that time, because there were not too many, the concept of association rules was just coming up, and people were looking. They had just started looking at its applications. There were not many algorithms which could find out the association rules. So at that point in time, a priori was considered as a very breakthrough algorithm. Okay, it was a it was rated as a very first-rate algorithm for computing the frequent item sets. We will just study that. Before that, that falls into this reduction of the number of candidates approach. But before that, I'd just like to take a minute. I'll just like to indulge uh, here for a minute or so on how to reduce the number of comparisons. So please see, FP tree algorithm was one of the algorithms that we used to do earlier in your course, but now that has been left out from the guidelines. So in that algorithm, what we did was we only maintained the frequent patterns. Okay, FP tree meant frequent pattern tree. We only maintained the frequent patterns in a particular tree-like hierarchical structure. Okay, the beauty was that this tree-like structure, data structure, it fit completely in the main memory. So, not requiring us to do things like vertical partitioning and all of the algorithm as we had discussed in the second case. And yet at the same time, the number of comparisons was reduced because as we descended from the root towards the leaf of a branch of the tree, automatically the most frequent items would appear on the top, leading down to the most infrequent, which were on the leaves. Okay, so we could just prune a particular level of the tree and get item sets, frequent item sets above a particular threshold. Okay, so that reduced a lot of comparisons. So these are the three techniques that can be, in theory, proposed for reducing the algorithmic complexity of frequent item set generation problem. We are going to look at the first technique in detail. As I told you, we will be looking at the a priori algorithm. So, what is the a priori principle? What was the basic principle that Mr. Rakesh Agrawal pointed out, which led to his recognition and this algorithm? Please see, the idea was very, very simple. You can look here. If a particular item set, let's say ABC, is infrequent, right? Or I should say the other way around first for you to understand. If let's say a particular item set item A, A, AB is infrequent, would ABC be frequent? Do you think that any of its supersets, let's say ABC, ABD, ABE, or any other, can be frequent? This is like asking you that if milk, let's say A denotes milk, and milk is very infrequently sold, okay, at my shop, then will milk and beer or milk and bread be frequent?
No, ma'am.
Obviously no, right? So if A is, if your item set, let's say AB is infrequent, then obviously all its supersets will also become infrequent. Okay, and this is the a priori's principle. Okay, let's see. So a priori principle, it is based upon exactly the same thing that I just told you, that it says the opposite, but it uses the same thing that I told you to prune the extra item sets. Okay, so the basic principle, the a priori principle itself says that if an item set is frequent, then all its subsets must also be frequent. In other words, for all xy such that x is a subset of y, if x is a subset of y, then the support of x of an item set x can never exceed the support of an item set y. Yes, right? For
Yes,
ex-
ma'am.
right. So this is known as the anti-monotone property of the support. This is known as the anti-monotone property of the support. Formally defined, uh, monotone is, what do we mean by, before we define what is anti-monotone property, let us discuss what do we mean by monotonicity. Okay, so monotonicity means that just the reverse key, uh, a measure f is called to be monotone, means upwardly closed, if for all xy belonging to J, where J is what? J is the power set of I, where I is the list, set of items. What is the power set of a particular set of items? Let's say if I'm talking about only two items, A and B, then their power set is A, B, and AB. That means uh, combinations, or all the combinations that can be generated from that set of items. Okay, that is the power set of a particular set. Okay, that is how the power set is defined in mathematics. So for all the item sets belonging to this power set, if x is a subset of y, monotone property says that the support of f the support of x should always be less than equal to the support of y. Okay, so what will be the anti-monotone property, or the monotone property was called the upward closure property, and this is known as the downward closure property. It would be just the reverse. Okay, which means that if x is a subset of y, for example, milk is a subset of milk and bread, then the support of Fy must not exceed Fx. Then the support of milk and bread can never exceed the support of milk. Is this clear? Is this clear? So what is support? What is the property that support follows? It doesn't follow the monotone property, as we've just seen with this small, very small example of milk and milk bread. It follows the anti-monotone property, and using this property, as you can see here, we are able to prune the entire part of lattice, which is a superset of, let's say, AB, if AB is found to be infinite. Okay, so you can see, very small and very simple principle, but such a big effect. Now, suppose AB is infrequent, then this entire part of the lattice goes away. We don't have to do the computations for this. Similarly, suppose BD was also found to be frequent, then another part of the lattice would also go away, right? We don't need to do any computations for those, right? And we are sure that we are not losing out on any frequent item sets at the same time, because we are just pruning the infrequent item sets. Okay, there is no point in generating the rules from all these item sets and then evaluating whether those rules are going to be interesting or not. Okay, is this clear?
Yes, ma'am.
Right. Very good. So I will take one more class next time, in which I will first of all illustrate the working of the a priori algorithm through steps, and then discuss the algorithm itself with you, and then maybe take up an example of the sort which is given to you in exams, uh, which will involve maybe the generation of association rules and all. Okay, so I'll build you up till that point, so that you're able to do this kind of question. If it comes in your exam, especially now in the OBE mode, is generally, of the entire 18.75, whatever marks your question has to be. Okay, is this clear? Right. So that is why I'm devoting the entire next class to this portion. After that, I think nothing more to be done from this chapter. Uh, just look at the guidelines. That I think we'll be able to finish this chapter the next time. Okay. And maybe even start the next chapter, that is the clustering. I'll share your link for the attendance now. Request you all to mark your attendance before you go.